So I'm pleased to introduce and welcome Adam Schlosser here. Adam is a senior research scientist and deputy director of the Center for Sustainability Science and Strategy at MIT. I think Adam fits very well in this community this morning, as his background is actually in meteorology, and he has a long and varied experience with numerical modeling of the climate system, spanning a wide range of complexity, from EMICS to full-fledged ESM to emulators. But as the name of the center that he is helping to lead suggests, his career has been about bringing this expertise to the integrated modeling of the Earth and human system to tackle problems of mitigation and adaptation in very different domains, always in this integrated approach, though, like hydrology, biodiversity, energy, of course, and at very different scales, from individual river basin to the global dynamic perspective. So he's going to describe some of it, I believe, in his talk, and focusing on what results, I think, from a program that has been supported over many years by the DOE MSD program, previously Bob Vallario and now Zhu Jing. So without further ado, I'll give the floor to Adam. Welcome, Adam.
Thank you very much, Claudia. It's a pleasure to be able to speak with you all today. And my talk today, I'll put it on full screen mode now to get things started. But as Claudia mentioned, my talk today, my intent is to really give everyone a very broad perspective of not only the DOE project that we've sat in for decades, but also hopefully to give you all a flavor for where our Center for Sustainability Science and Strategy, where it sits now, where it's been, where it has been in the context of DOE research. And I think, as everybody on this webinar session today can appreciate, we're in a very sort of uncertain climate right now, so to speak. And I think we're all trying to sort of understand where our research sits. And what I hope is, from what I share with you today, it'd be very broad strokes. I really won't have time to get into details, but very broad strokes of what we do. And I'm really looking forward to, I'll be attending the E3SM All Hands meeting in a couple of weeks. And so I hope what I share with you today will really be just sort of fuel for deeper dive discussions within all the breakout sessions and the plenary sessions that are coming up in the E3SM meeting in a couple of weeks. So to sort of get things started, our project under the DOE multi-sector dynamics program is about sort of compounding influence, compounding stressors, sort of co-evolving risks, not just physical risks, but transition risks, and what could also be described as termination risks. And obviously, these all fit in the scope of prediction. And as some of these sort of tongue-in-cheek quotes suggest, prediction is a very fickle beast. I think there are a lot of challenges that we can all appreciate, not just in the Earth system and climate space, but in the spirit of multi-sector dynamics. We also have to think about society and human systems, and that's sort of where the bulk of our research sits. So again, what I'd like to do today is just to give you a brief introduction and background of our center, give you a little bit of a historical perspective, give you, again, a very broad overview of our project, just sort of where it sits, some of the bigger nuggets that we're trying to push forward. And hopefully what I'll close with are just some bullets of where it seems like DOE, BER, and MSD, where their priorities may be moving. I know it's a very dynamic target right now, but in terms of where that looks to be going, hopefully the list that I provide will again provide fuel, not just for conversations today, but hopefully in a couple of weeks when we all get together down in the DC area, we could talk about that further. Again, by way of just introduction and background, again, I sit in what's now known as the Center for Sustainability Science and Strategy. We were once known as the Center for Global Change Science, and in the particular lab that I sat in, and the lab that the DOE project that we work under sits, we were known as the MIT Joint Program on the Science and Policy of Global Change, and the work did pretty much what it sounds like. We're very much a collection of Earth system climate-oriented scientists like myself, as well as economists, social and policy-oriented researchers. And we're very much in the business of making sort of global predictions of big changes in the global environment, particularly as they relate to human interference of the climate system, and trying to understand what are the best strategies and pathways for mitigation. Not only what sorts of pathways can meet certain climate targets, but what are the energy transitions and the deployments at scale that make sense, and what are their cost-effective pathways, and what are those solutions. So that center and the joint program was born out of efforts of Ron Prinn and Jake Jacoby, who were the co-founders, and this dates all the way back to the early 1990s. So we've been around for a few decades. That program got its start with the help of DOE. At the time, I believe it was called the Integrated Assessment Program, IEP. And again, we very much sat in this sort of integrated assessment space. Along around a couple of years ago, we made a change to, again, this Center for Sustainability Science and Strategy, CS3. It still embraces a lot of the work that we do, and that's really very much carried forward. I would say the biggest sort of salient changes or distinctions between CS3 and, again, our predecessor lab is that we're bringing very much more into the lens of our research this notion of well-being and health, and how humans and also the natural and managed environments play into all of that. And so thinking a little bit more beyond just the climate targets, but thinking a little bit more holistically about other challenges, other pathways that that we need to be cognizant of for sort of an overall prosperous and sustainable society, if you will. So I'll touch on that a little bit, but in the spirit of E3SM and the legacy of a lot of the work that we do, one of our workhorse tools that we've had with us for since the beginning of the center, of the joint program as well, has been this integrated global systems model, which you see on the right here in that schematic. And this integrated global systems model, or IGSM, has been used in a series of outlooks that we've provided. These outlooks have been produced from anywhere between every year to sort of a 2-year cadence. We're kind of on a 2-year cadence right now. So we'll have one coming out in 2025 this year, by the end of this year. And again, as I mentioned, the model really sits in this sort of integrated assessment space, and it does align very much with a lot of the IPCC assessments. What we do is we think about various scenarios, and we have sort of 2 big scenarios that we think about, which are current trends, which is where we just sort of look at where are the current policy settings now that are in play, and if we were just to carry those forward, what would the world look like? And then we think about sort of, again, very much aligned with the IPCC scenarios, is what we think is sort of our most likely stabilization pathway, and what are the probabilities surrounding all that. So we use a joint probability method, Latin hypercube sampling, not only within the climate system, but within the human system, the economic models that we exercise. And we provide a distribution of outcomes. We've articulated these in what we call greenhouse gamble wheels, which you see on the right there. And these have been sort of very effective communication tools to at least sort of convey sort of the global overall risk. But again, just to give you a sense of historically where we're coming from, this is very much in our wheelhouse, no pun intended. This is very much what is one of our recurring and sort of showcase outputs in terms of reports. And this is just going to give you an example of the sorts of things that we've done. And it very much aligns with, I think, a lot of the IPCC work. We generate thousands of different members of and ensembles of outcomes, and we look at things, again, like in the current trends, where we think we're headed. We think about overshoots and what are their ramifications and what are their impacts. And again, it all feeds into this outlook report that's come out. So to kind of set the stage for DOE and again, how we perhaps align closer with E3SM's efforts. This is just sort of a bulleted list of the successes, milestones of our MIT project under the multi-sector dynamics program. And as I think I've already articulated, we have built this sort of Earth system model of intermediate complexity. Since we're generating thousands of different members, we have to sort of provide an efficient tool to do that. So we've, over the years, built this sort of intermediate complexity model that has process level representation of what we think are the important aspects of the Earth system and the climate system. This has to be linked to a global and regional economic modeling approach, which I can touch on in later slides. It all builds into this uncertainty and probabilistic risk-based projections of global change. From that, we have branched out into a lot of impact channels. As Claudia mentioned, we've done a lot of work in water resources, both global and getting down to sort of the basin level scales, which again, hopefully I'll have time to touch on in slides that follow. We've done some great work with collaborators at PNNL to take land use projections that have provided our economic model and bring it down to, again, to local scales that our impact models can look at. As I mentioned before, the push for CS3 has really been in this area of broadening our perspective of targets, of environmental targets, if you will. And so to do that, we have built a capability where we're integrating into atmospheric chemistry models to look at co-benefits and co-evolving risks in the case of air quality and impacts on human health. A lot of our work too has preceded, I think, the heroic efforts of CMIP7 to get sort of active carbon models into the IPCC scenario business. With our intermediate complexity model, we've been able to look sort of explicitly at nitrogen and carbon cycles in the biosphere and how they play out, and again, in an emissions-driven scenario pathway for developing future projections. So that's something that we sort of laid the foundation for, and it's great to see things like CMIP7 doing these sorts of efforts. So again, that's kind of a quick history of the project. And to move into, again, the more recent developments of the DOE project, the DOE program, multi-sector dynamics, around the time of about 2016 election, what a coincidence, we were asked to sort of redefine ourselves and rethink how our research really speaks to, I guess you might say the changing mission and directives of DOE at the time. And what we did was to think a little bit more in terms of a testbed scenario or a testbed capability, and again, really try to push what was the original intent of our framework, which was thinking more globally. But again, as I mentioned, we were pushing these sort of impact channels, and we sort of evolved into this framework of thinking about upstream, downstream impacts of, again, sort of various landscapes of energy, water, land, air, nexus, risk pathways. And it led us to this idea of focusing on the Mississippi River Basin and using our tools to better understand not just sort of the slowly evolving risks, but also perhaps more rapidly evolving risks and stressors that evolve within the upstream downstream connections of the Mississippi River Basin. And so that's led us to this new research thread that we have under MSD. We are currently sitting right in the middle of our 5-year project, and the tasks that we laid out are highlighted here. As I mentioned, we're really trying to sort of advance our system of systems framework. We have a number of areas where we're pushing, which is sort of developing screening sort of triage level platforms, developing methods that look across massive ensembles to sort of look at scenario discovery patterns, and also using ML. And I guess no talk these days can be complete without mentioning AI and ML, but we're using methods in the ML space to try to get at extreme events and, again, how they impact all of these systems. And again, we're still focusing on the Mississippi River Basin. We're building this sort of test bed capability to look at not just the energy system, but as it relates to other infrastructure landscapes, such as transportation, and again, all bringing that all into sort of the human society relevance and impact. And ultimately, for our third task, our hope is to have an ability to not only flexibly look across all of these interconnected systems, but to be able to perform a series of stress tests, again, that speak to broader mission goals of DOE and the BER and MSD. This just gives you, again, a very, very broad, quick stroke of all the tools that we've been developing. Again, going back to sort of our workhorse model framework, we have a model of the human system. It's a computable general equilibrium model of not only the global economy, but we can bring it down to regional scales. We have a model that works at a state level over the US. And this is connected to, again, our physical systems model, our Earth system model. We operate not only this intermediate complexity model, but as I'll get to in slides that follow, we've been working on connecting this model to some of the more traditional IPCC class models, such as CESM and E3SM, and making subsequent connections to regional climate models and air chemistry models, such as GeoChem. This is all also being enhanced by other more efficient ways of downscaling and pattern scaling events and features of the climate system that we think are important to all these systems. So again, this is all just sort of one big package that we're kind of moving forward in stride as we need it and as the research requires. I guess if there's one slide that I'm hoping you can all take away from you can take away with you from this presentation is this slide, and I think it speaks pretty closely to other sort of test bed frameworks that I've come across or that's been sent along to me in terms of DOE sort of redefining their mission statement and their priorities. And so again, in putting all these tools together, what our project is really aiming to do is to build this sort of flexible design and systems of systems design to provide a test bed for these interconnected systems. And because obviously this is a DOE project, we do have a real focus on the energy infrastructure, particularly the grid resilience or the grid infrastructure, but recognizing, of course, that there are other connected systems that deal with, again, human impacts, water resources, air quality, land use, land productivity. How all this comes together is very complex and requires different details at different levels for different modules. I think there are going to be some opportunities where we can use emulators to speed up all of this, but we're taking very careful and deliberate steps to do that. I'll mention a few, hopefully, in the slides that follow with the time that I have left. But again, ultimately, all of this is being put together with the vision that we're recognizing that there are not only slowly evolving changes that not only include Earth system scale changes, but global and regional socioeconomic forces. But there are also very local scale extreme event impacts that factor into all of this. And the ultimate goal is to provide insights, quantitative insights in all of this, keeping in mind, of course, that one has to be very cognizant of the fact that we can't rest upon one outcome from one model or one configuration. We really have to put together a probabilistic risk-based presentation of all of this. So what I'd like to do with the time that I have remaining is just to give you a little bit of a deeper dive quick deeper dive of some of these threads that we're working on. So as I mentioned before, we have on the left here our workhorse version of our human Earth system model, and we've been making strides, and we have a paper coming out that's imminent, that will be submitted imminently, that presents our approach to take our intermediate complexity model and human Earth system model and link it to, again, a more traditional version of an Earth system model, IPCC class style model. And we've done this with the community Earth system model. We are currently working to do the same for E3SM. believe we have it for version 2, so I think we have to make connections with version 3. But the idea here is to use, again, our framework of using an emissions-driven model, using those concentrations then to force, again, an IPCC class style model under different scenarios. Again, this is very much aligned with our current trend scenario and our accelerated action scenario from our outlook. But the idea is that we can provide sort of details into more impact-oriented output. So what you here is looking at is just a range of outcomes across different scenarios under different resolutions, with CESM being driven by, again, the concentrations from our emissions-driven model, looking at various horizons. And one might ask, well, why are you using CESM? One of the opportunities, shall I say, that presented itself with CESM is that we had developed a method where we were able to nudge the climate sensitivity of CESM. And we thought that was a nice salient and distinct way of adding to our portfolio of looking, again, at various outcomes, various probabilities, distributions of outcomes. And this is very much born off of the approach that we used in our intermediate complexity model, and it just happened to fit into CESM really well. So again, this is just an example of, say, looking at one particular scenario, which is the current trend scenario, for a particular time horizon, sort of the near term, which is out to a couple decades. And we're able to look at things like, how does an extreme event outcome vary, or how sensitive is it to changing or nudging the climate sensitivity from low to high? And how does it size up against just scrambling the initial conditions? And this is work that will be highlighted in the paper that I mentioned that's forthcoming. But again, this is just sort of a high-level presentation or example of what we can do with that framework. Along the lines of emulators and sort of more efficient tools, we have been working in the space of air quality so that, again, we can speak to our broader vision of not just thinking about climate targets, but more sort of human impact, human health targets. And so what we've done is we've developed this tool for air pollution scenarios, TAPS, which feeds directly off of our economic and intermediate complexity model simulations, where we can look at various pathways that not only look at just what's the impact of air quality from these climate targets, but if we were to think about sort of, say, maximum feasible reduction, so that MFR bars that you see there, this is sort of what you might imagine would be the maximum feasible reduction in some of these precursory concentrations of trace gases. We can see that there's a lot more that we can do that go beyond just traditional climate targets. And again, this is a very efficient tool. It's emulator based and provides us a very rapid response of looking at various scenarios. We've done the same with things like extreme temperatures. This is an example of work that, again, the submission of this method is imminent. And we've used an ML-based procedure where we've looked at historical patterns and trends of extreme temperatures at a local scale and have linked it to our global model. And it allows you in a very efficient way to select any region of interest, down to sort of sub-state level to county level, and look at how various scenarios will play out according to, again, this particular metric, which is just daily maximum temperature. And you can look at the impact of sort of a current trends to a sort of a more aggressive mitigation scenario and how that plays out. And it includes uncertainty with the shaded area. It's got everything that we think is important to convey this types of information. And there's really nothing limiting about this. We've picked daily maximum temperature, but I think, as any of you in the audience here can appreciate, with any of these types of ML-based methods, if you have the data, this sort of procedure can sort of easily be adapted and flexible and applied to. So we sort of view this as an opportunity to think and look at other, again, impact variables or impact-oriented variables. Quickly, since I'm running out of time, as I mentioned before, we've had a really successful collaboration with PNNL to take our economic region scaled predictions of land use change and used a tool called the meter to bring it down to sort of more granular levels. We've had some interesting findings that have been recently published, noting that in certain in certain plausible pathways, the U.S. actually becomes somewhat competitive in terms of providing livestock or meeting livestock demands. And so we see that there's a possible pathway where pasture land could be expanded quite dramatically in the future, making certain assumptions. But again, this fits under the whole probabilistic plausible pathway. This is just one plausible outcome among many. But again, it highlights an interesting storyline using this type of tool. Under our project, we're also, again, as I mentioned, thinking about things like transportation systems. We've set the stage for, again, enhancing our framework to think about this. Paper has recently come out that sort of articulates a lot of this. There's a lot in there that doesn't just relate to climate-oriented outcomes, but it looks at the whole gamut of potential stressors. And again, we're trying to move that forward. And we have a particular focus on the Port of South Louisiana. We've made some really nice connections with the management and operations at the Port of Louisiana. And we're really hoping that a lot of the data that we'll receive from them will allow us to make a nice stride by taking, again, a lot of our, what you might argue, more macro scale tools, bringing it down to a real local and an impact relevant scale. Similarly, we're doing a lot on energy system. I'm running out of time, so I'm just going to sort of whiz through these. But again, we've got work that's using our tools to look at energy gaps based on a whole wide array of plausible futures. There's paper out on that. We have a lot of work going on in water resources. We have a system that looks at not just the availability of water, but also the quality of water. We have a parsimonious model that allows us to look at various nutrient loadings. This framework also allows us to add things like microplastics and forever chemicals into the framework, so we can think more broadly about water quality. It allows us to get down to very granular scales. We can look at tipping points. This is just, again, a sample of what we can look at under various plausible futures. We see very clear tipping points in dissolved oxygen, which basically kills wildlife, aquatic life in a stream. And these can be avoided under other scenarios that embrace sort of, again, these climate mitigation targets. So there's sort of clear co-benefits that we're getting at very granular scales. So with all that, I'll stop here. This is just a recap of a lot of the capabilities that I've scanned over. And what I'm hoping this really does is to sort of set the stage for not just conversations that we have today, but again, I'm really looking forward to attending the meeting in a couple of weeks and hopefully seeing all of you that are here today and really talk a lot more about this in more detail. And again, I do appreciate, and I think we all recognize that a DOE BER is going through a big transition here. So hopefully we can move together forward on all this. And again, I appreciate your time and look forward to talking more about this.
Wonderful. Thank you.